Good morning everyone. Welcome to today's class. Today we are going to deal about Horizon's characterization of normality. It's one of the main result in a separation axiom. It actually says when a space is going to be normal and with that condition the space is always normal. That is, it's an if and only if condition. Horizon's characterization of normality. 3.1 proposition. Let A, B be subsets of a space X, and suppose there exists a continuous function f from x to closed interval 0, 1 such that f of x is equal to 0 for all x belongs to A and f of x is equal to 1 for all x belongs to B. Then there exists disjoint open sets U and V such that A is contained in U and B is contained in V. Proposition says that suppose you have got a space and you have got two subsets, that's A and B, and you're having the closed interval here, it's AB or the 0 1, so this is my 0 and this is 1. Now suppose if there exists a continuous function from this space X, so this entire space is X, so this space X to our closed interval, so the function is from here to here, mapping such that in this entire set is mapped to f of I'm mentioning this as B and this is A. Now entire set A, it's on the reverse, right? Make this as A and this is B. So this as A, this my A and this may B. Now this entire element in A is mapped to 0. The 0 entire element is mapped to 0 and here entire element is mapped to B. If this the condition means we can have two disjoint open sets in U and V such that A is contained in U and V is contained in, you can find two disjoint subsets. Now the simplest way of proving this is that, see, this is the proof. That is, we can take open sets in this closed interval 0 1 such that one is containing 0 and another is containing 1. If we are taking this as an open set, then you can take its inverse image. Since f is continuous, this open set will map to an open set and definitely that will contain this A. So let us go to the proof. We simply choose any two disjoint open sets G and H in closed interval 0 1 containing 0 and 1 respectively. So G is an open set in closed interval 0 1 which containing 0 and H is another open set in closed interval 0 1 which containing 1. And we will set U as F inverse of G and V as F inverse of H. Now our claim follows the property of F. Y means you have taken G as an open set containing 0. So when you are finding F inverse of G, definitely it will contain your set A because all the elements in your set A is mapped to 0. And we have taken G to be an open set and F is continuous. So F inverse of G should be also open. In the same way, you have taken H as an open set which containing 1. So when you're taking its inverse image, since all elements of B are mapped to 1, B is contained in F inverse of H. And you have taken H to be open, F to be continuous, F inverse of H should be open. So you have got two open set U and V such that the condition is A is contained in B and B is contained in V. A is contained in U and B is contained in V. Now suppose if you are replacing A and B be subset of a space X, instead of that, suppose you are taking A and B are closed sets. Now this property is hold means what you can conclude. I repeat the question. If A and B are closed sets and that will satisfy this property, then what you can conclude? The conclusion is nothing but the space is normal, because this is the condition for normal space we would get whenever A and B are closed sets. So corollary. If a space X has the property that for any two mutually disjoint closed subsets A and B of it, there exists, so you're taking closed subset. There exists continuous function f from x to close level 0, 1, taking the value 0 at all points of A and the value 1 at all points of B, then x is normal. By previous proposition, if this is the case means you will have two disjoint open sets U and V such that your closed set A is contained in U and closed set B is contained in B. So it will give you the normality condition or the normal condition. So it follows immediately from the last proposition and definition of normality. Exactly, if you're putting an if and only if condition for this, means you will get the Horizon's characterization of normality. So passing to Horizon's lemma. A topological space X is normal if and only if it has the property that for every two mutually disjoint closed subsets A and B of X, there exists a continuous function f from x to close level 0, 1 such that f of x is equal to 0 for all x in A and f of x is equal to 1 for all x in B. So the Horizon's lemma says that a topological space is normal if and only if whenever you take two closed subsets A and B of X, we can able to find a function f from x to close level 0, 1 such that it will map every element of A to 0 and every element of B to 1. Then the space is normal. Now conversely, if a space is normal, if a space is normal, then we can find for any two closed set a function f from x to close to 0, 1 such that every member of A is mapped to 0 and every member of B is mapped to 1. So an if and only if condition. So first we want to prove that if such a function is existing, then the space is normal. That we have already covered, since the corollary says the same. X is the property for any two mutually disjoint closed subsets A and B of it. There exists a continuous function with this property. Then X is normal. So we will say that this is the sufficiency part. So the sufficiency part of the theorem is, or the lemma is, we have already proved. So sufficiency of the condition is established in corollary 3.2. Now the necessity part. Necessity part, for proving this we need two lemmas. So lemma 1, What we are going to do is we have to prove that we have proved if a function is existing, it is normal. And conversely, we want to prove that if it is normal, there exists a function, continuous function f, which will map every element of the closed set to one closed set to 0 and another closed set to 1. So for the necessity part, we want to assume that it is a normal space and you want to get a continuous function. So here is the first lemma. In this lemma, what we are going to do is, instead of proving f to be continuous, we will prove that f to have certain properties in terms of an index set. Okay. So 3.4 lemma, let f from x to close level 0 1 be continuous for each t belongs to R. F from x to close level 0 1 is continuous for each t belongs to R. Let ft is equal to set of all x belongs to x such that f of x is less than t. First we consider the function from x to close level 0 1. Next what we are going to consider is for each t belongs to R, ft. This set has to be very clear. So ft is equal to set of all x belongs to x such that the function value of x is less than t. X belongs to x such that function value of x is less than t. Then the indexed family, consider all such ft. So ft such that t belongs to R has the following property. First property is ft is an open subset of x for each t belongs to R. ft is an open subset of x for each t belongs to R. We want to prove that this set is open. Now ft is equal to empty set for t less than 0. ft is equal to empty set for t less than 0 and ft is equal to entire set x for t greater than 1. And last condition, for any s comma t belongs to R, s less than t implies fs closure is contained in ft. For any s comma t belongs to R with s less than t, then fs closure is contained in ft. And moreover, so it's the repetition, so you can skip anyone. So I'm better this, I should avoid this. And the fifth property, moreover, for each x belongs to x, fx is equal to infimum of t belongs to q, x belongs to ft. Fx is equal to, fx means the function. So fx we are defining in terms of your ft's. So fx is equal to infimum of t belongs to q such that x belongs to ft. X belongs to ft. You collect those x which belongs to ft. Now you take the ft's t part. T belongs to q. Now we take infimum of that value. You will get your function f of x. So first we want to prove that ft is an open subset of x for each t belongs to R. See here exactly you are taking f of x which is less than t. So you can go for minus infinity t, right? The set minus infinity t, and you can connect that with ft. So note that ft is the inverse image under f of the set minus infinity t. ft is the inverse image of f of the set minus infinity t. Now which is open in R? Minus infinity t is open, f is continuous, so its inverse image is also open. So ft is open. Thus condition 1 is true. Now 2 and 3. Ft is equal to empty set for t less than 0 and ft equal to x for suppose t less than 0. T less than 0 means you will get ft such that x belongs to x such that f of x is less than 0. Since we are taking the value from 0 to 1, below 0 value should be empty sets. So first condition, ft is equal to empty set for t less than 0. And second thing, since the value is taken from closed level 0 to 1, what you can conclude is for t value greater than 1, t value is greater than 1 means you are having your ft as set of all x belongs to x such that fx value is greater than 1. So you will get the entire set x. See, from x to be continuous for each t. So indexed family. So any value you will take from x, its fx value is greater than 1 means you can get the entire set x. So 2 and 3 follow easily from the fact that f takes values in the unit interval. So 2 and 3 also we have discussed. Now for the fourth one, for any s comma t belongs to R, s less than t implies fs closure is contained in ft. So let R be any value or any number between s and t. That is s less than r less than t. S less than r less than t. And let C is equal to set of all x belongs to x such that f of x is less than or equal to r. X belongs to x such that fx is less than or equal to r. Then fs is contained in C because fs means your value is set of all x belongs to x such that fs means, go for the definition. Yeah, x belongs to x such that fx is less than s. Since s is less than uh, r, we will have this set fs should be contained inside C, and similarly this set is contained in ft. Now C is closed, right? Since we are taking less than or equal to quantity, C is closed in X by continuity of F. So what do we have? Fs closure should be contained in C, which implies Fs closure is contained in Ft. So you have seen you have taken an R in between S and T, and you have defined a set C is equal to set of all x belongs to x such that fx is less than or equal to R. Now fs is contained in C, which is contained in ft. This you can easily get while comparing the definition of ft or fs with this set. And now we are saying that the set C is closed. It's evident since fx is less than or equal to R. So it's closed. Now this is closed means this closure should contained in this closed set, and this closed set is contained in this. So you can conclude that fs closure is contained in ft. So that we want to prove if s less than t, then fs closure is contained in ft. Now for the fifth one, we want to prove that for each x belongs to x, fx is equal to infimum of t belongs to q such that x belongs to ft. This is the function. So for fifth one, let x belongs to x and let gx be the set set of all t belongs to q such that x belongs to ft. It's nothing but what we want to prove. Alright? See, t belongs to q such that x belongs to ft. So t belongs to q such that x belongs to ft. Now we want to prove that f of x is equal to infimum of this gx. So fx is equal to infimum of gx. So gx is non-empty. First one, gx is non-empty since t belongs to gx for all rational t greater than fx. Since t belongs to gx for all rational t greater than fx, that follows from the definition of ft. Also, t greater than or equal to 0 for all t belongs to gx. T greater than or equal to 0 for all t belongs to gx. Since if it is less than 0, we will find that it is an empty set. So, which implies gx is bounded below. So, for all t greater or equal to 0, all t belongs to gx. So, gx, our set, is bounded below. Now let y is equal to bounded below means it should have an infimum. Now set y is equal to infimum of gx. Now we want to prove that f of x is equal to y. Now for any t belongs to gx, x belongs to ft. Definition: t belongs to gx means x belongs to ft. By definition of ft, x belongs to x such that fx is less than t. So its value should be less than t. For any t belongs to gx, x belongs to ft. F belongs to xt, the meaning is f of x is less than t. X belongs to ft, meaning is f of x is less than t. Therefore, f of x is less than or equal to infimum of such t's. So f of x is less than or equal to infimum of such t's. So f of x is less than or equal to infimum of gx. So you got f of x is less than or equal to infimum of gx. That is, f of x is less than or equal to y. F of x is less than or equal to y. Now we want to get the reverse implication. That is, y is less than or equal to f of x. Then we can conclude that y is equal to f of x. But what is y? Y means infimum of gx. Now suppose f of x is strictly less than y. Okay, f of x is strictly less than y. Let q be a rational number between fx and y. This is the condition we can find a, if this is f of x, so there exists a q less than q which is less than your y. Now this q less than y. Hence x does not belongs to fq because fx is less than t you have taken. So it does not belongs to fq. So fx is greater than or equal to q. So fx is greater than or equal to q. This follows from the definition of ft. Ft means set of all x belongs to x such that f of x is less than t. So x less than belongs to fq means value of f of x should be greater than or equal to q. Now we have got fx is greater than or equal to q, which is a contradiction. Reason is, since q less than y and here have got f of x is less than y and you have taken an element in between fx and y. So fx is greater than or equal to q means it's not possible. So which is a contradiction. Hence we get f of x is equal to y. So this is a short class. That means we have discussed only 2 or 3 results. Only Horizon's characterization of normality. Only we have discussed. In this, we have proved is one part. That is the sufficiency part. Necessary part is remaining for us. And we have for the proving necessary part, we need 2 lemmas. In that one lemma we have proved. That is, if there is a continuous function from x to close to 0, 1 for each t belongs to T, this indexed family of sets have the following properties. First property was this set is open. Second one was this will become empty set for t values less than 0, and this will become your x and your x for t values greater than 1. And if s less than t, fs closure is contained in ft. And the last one, fx can be defined in terms of your ft as fx is equal to infimum t belongs to q such that x belongs to ft. So I hope you will follow me, and thank you for your patient listening. See you in the next class.